Let's imagine that you're about to sell your house. Now you have the task of determining how much your house is worth on the current market. You decide to check online for prices and living areas of houses nearby. You put this data in a graph with the house size against the house price. Given the size of your house, you could eyeball an expected price for your house. But a more elegant solution would be to fit a model on your data and use this model to predict the price of your house. One simple model which could be used for this task is a linear regression, where you simply draw a straight line through the data points. But how should you draw this line? Let's take a look at one of the houses you found online, which is the second last point in your graph. Our red line predicts a value over there. This means that our model is off by this much. The difference between the predicted value and the observed value is called residual, or sometimes also called error in machine learning. There's actually a difference between the term error and residual, but let's ignore this for now. There are two popular methods of using these residuals. One of these methods is the L1 loss, in which you minimize the absolute magnitude between the predicted value and the observed value. The two common flavors of L1 loss is the mean absolute error and the sum of absolute errors. The other method is an L2 loss, where you minimize the difference between the observed value and the predicted value squared. Two common versions of an L2 loss is the mean squared error and the residual sums of squares. So how do these methods differ? The L1 loss doesn't care if you make a few small mistakes versus one big mistake, whereas the L2 loss penalizes a large error way greater than a few small errors. For example, let's say we have a case where we have 5 residuals of size 1 versus a case where we have 4 residuals of size 0 and 1 residual of size 5. The L1 loss assigns a value of 5 in both cases, whereas an L2 loss calculates a value of 5 in the first case and a value of 25 in the second case. So as you can see, an L2 loss actually penalizes bigger mistakes. The second question is, which of those two methods is the best? One way to check this is by actually taking a step back and think about what it actually means to have the best model. One elegant method to determine which model is best is by saying which of those models is the most likely to have reproduced this data. This is what's called the maximum likelihood. This sounds of course very abstract, so let's illustrate this with a very simple example. Let's say we are playing a game of dice with a friend. When it's your friend's turn, you decide to go for a toilet break. When you come back, you find that your friend has thrown 4 times a 6. Your friend says that he or she obtained these values by simply throwing one of his or her dice 4 times. This of course seems very impossible, so you decide to investigate what's going on. You find that he or she has 3 different dice. One regular d6, one d6 with 1, 2, 3, 1, 2, 3, and one die with 1, 6, 1, 6, 1, 6. You set out to calculate which of these dice is most likely to have been used by your friend. For the first die, the probability of throwing 1 6 is 1 in 6. So the probability of throwing 4 times a 6 is 1 in 6 times 1 in 6 times 1 in 6 times 1 in 6, which equals roughly 1 out of 1300. For the second die, there's no 6, so the probability of throwing a 6 is actually 0%. For the last die, the probability of throwing a 6 is 50%. This means that the probability of throwing 4 times a 6 is 1 in 6, which equals roughly 6%. This means that it's most likely that your friend has used the third die. This is what's called the maximum likelihood. Now let's apply this approach to our data and compare two cases. A good fit, represented by the red line, and a bad fit, represented by the magenta line. Let's assume that this data is generated by a process in which the samples are generated with an error which is normally distributed. This means that you have a nice bell curve around the fit, where data points further away from the line are way less likely than points close to the line. I've illustrated this distribution around the fit in this plot over here. And here in this plot, the same thing, but centered around 0, which is actually expected house price. The differences between the fit and our observed values is called the irreducible error. This is because there's no way to actually minimize this error given the features we have. If we have more features, like the state of the house, or the size of the garden, or the number of rooms, we might be able to actually reduce this irreducible error. But given our features we have now, there's no way to do this. Of course, some part of this irreducible error is really hard to reduce, because this might be dependent on the mental state of the set or something. The mathematical formula that describes this bell curve is this formula over here, where the sigma squared value is the variance, where nu is the offset of the distribution, and x is the quantity in question, which is in our case the price of the house. Let's now use this formula to determine which line is the most likely. So how do we use this function for our problem? First, we replace the nu, which can be calculated with y equals ax plus b. This notation might be familiar to you because it's kind of the way how you write it down in high school. A more common way to describe this function is using the w and b in machine learning, where B represents the offset in the vertical direction, which is also called the intercept in statistics or the bias in deep learning. A or W is the slope of the model. In other words, how much a feature contributes to the model. This term is also called the coefficient or the weight. Another way to write this down is using the statistical approach, where the intercept is beta hat 0 and the coefficient is beta hat 1 for the model. Here, the hat actually indicates that we're approximating the true beta, meaning that we're trying to find the true coefficients. However, of course, we do not know them, so we say beta hat instead of beta. We will actually be using this notation because it will be cleaner later on. Because it's very important that you understand this formula, let's relate this function one more time with our data. This formula allows you to calculate the probability density, which is proportional to the probability of a rough value. Let's take this house as an example. We know the observed price and we know the observed size of the house. When we fill in these values x and y with a certain variance, we can calculate the probability density of this exact observation. This is actually very similar to our simple case with the die, where the probability of throwing 6 is 1 in 6 when you're throwing with a normal d6 die. However, there's actually a notable difference. Where it's very likely to throw exactly 6, it could actually be very unlikely to have a certain house price. Luckily enough, this doesn't really matter for what we want to do. The formula we are using right now is actually quite fine, but let's change it once again using linear algebra notation. This is because linear algebra makes things more compact. If you do not understand this notation, it's all fine, because it doesn't really affect the explanation. But this notation makes the formula a bit more general when we're dealing with more features. What we can do now is using the probability density function to predict the probability of observing all the data points. You do this by multiplying all the probabilities of all the observations together. This formula might actually look quite scary, but it's the exact same thing what we did with the die game. In the case of the die game, we multiplied the probabilities of throwing 6 for every die we threw. In the case of the house data, we multiply the probability of observing a house given normal distribution. This symbol over here might look scary, but it just means that we're multiplying over multiple samples. In the case of the die game, we calculate this formula for the 3 different dice. Of course, we could also do this for the houses, where we draw many different lines and calculate the likelihood and pick the best one. Of course, there's a better way of finding the best line instead of trial and error, but that's a story for another video. Now we know all of this, we can finally make the push to get our goal of this video, which of course is that we want to know if it's better to use the L1 loss or the L2 loss. So one way of doing this is actually to find the maximum likelihood of this function for every possible line. Another way to do this is actually using the maximum log likelihood. This actually also works for different transformations as long as they are positive monotonic. So why do we actually want to use the maximum log likelihood instead of the maximum likelihood? This might sound like we just moved the problem to another problem, but we actually simplified the problem by a lot. Because of a trick you can do with log values, where the log of different values is the same of log of values individually summed. This transformation usually changes our formula to something which is way simpler. Now we can also combine another trick. Because we just want to find the max, we actually do not care about constants. So we can remove the 2 constants in front of this formula. And we can also remove the constant in front of our summation. This is because these constants have no effect on the final result. By doing this, we completely remove the variance term of our equation, which is a huge help. And now we end up with this formula over here, where the log likelihood is proportional to a negative sum of squared errors. Maximizing this equation is the same as minimizing the sum of square errors. And lo and behold, we derive the L2 loss. This means that given these conditions, the L2 loss should be the best. Of course, this all sounds great in theory, but does this proof also hold up in experimentation? To test this, I fitted different lines in synthetic datasets, and yes, in most cases, the mean squared error has beaten the mean absolute error. So does this mean that mean squared error is always better than mean absolute error? Well, no, because we made one major assumption, which is that our data is normally distributed. However, this is not always the case. We might have the situation where our data is way less perfect and not normally distributed. In these cases, the MSE might actually underperform compared with the MAE, or maybe another loss value. Okay, done. This was actually quite an intense video to make. If you liked it, like this video. If you have questions or remarks, leave it in the comment section. And hopefully see you in the next video. This video is part of my in-depth machine learning course. The course is currently in early access, which means that new lessons and material are being released every month. Right now, there's also an early bird discount for early supporters. The goal of the course is to help you build a deeper understanding of machine learning, so you can develop real intuition, not just following tutorials. It's taught top down, making it accessible for different experience levels. We dive in the math, the stats, and why and how behind the models, backed by clear visualizations and hands-on examples using both real and synthetic datasets. If you want to support this kind of content, or if you are serious about learning machine learning, check out the page in the description below for more information.